Hello, everyone. Welcome to our session. I know this is the first session after lunch. I hope this topic is interesting enough to wake you up. I'm Ji-Hong, and this is Wimo. So we are here to talk about some of the work we have been working on at Huawei, specifically CarbonData. It's a new Hadoop file format designed for faster data analysis. So to give you an outline of the presentation, first we're going to share some common use cases we see and motivations. What motivates us to develop a new file format to answer the question of why. Then we're going to deep dive into the format itself and see how data is laid out on disk and how it works. So this is answer question of what and how. Then we're going to touch on some frameworks we integrated with CarbonData. After that, Wimo is going to share some early test results we collected, and followed by a live demo. We're going to wrap up the presentation with a future plan of the project. So at Huawei, we have our own Hadoop distribution. So we have seen some typical use cases from our enterprise customer. So one type of use case we have seen is more or less like a full table scan, which is a big scan which touch a lot of majority of rows in the table, and commonly involve aggregations. So but require a fast batch processing. Only fetch a few columns of the table, but not all of the columns. And some common uses scenarios we see is ETL jobs and log analysis. You probably already figured this is a sweet spot for columnar storage. So column storage will shine in this type of analysis. Another use case we like to share is OLAP style query, which performs a multi-dimensional data analysis. It commonly involves aggregation and joins, roll up, drill down, slicing, and dicing. Low latency ad hoc query is very common here. Some common usage scenario we see like a dashboard reporting, fraud analysis, or ad hoc analysis. So we have in the market MPP database, traditional MPP database are the player here. The third use case we like to share is a random access. What we mean is it involves a predicate filtering on a range of columns. It might be a full row key, like a primary key filtering, or a range of keys, combination of keys. It's generally a narrow scan, which you only touch a very few rows of the table, but you might fetch all columns. As the result set is so small, so generally you're expecting a very low latency, second or sub-second level is very common. Like an operational query to answer, customer complaint calls, you need to act quickly. User profiling to understand the user's interests, things like that. So to summarize the three type of use cases, we see a sequential access, which is a big scan. Column storage is the key here. Random access for narrow scan, edge-based system is probably the big player for big data to be able to do a fast primary key lookup. OLAP style query involve multidimensional analysis. Traditional MPP database is the player. But we haven't seen any file format or storage system can do a good job of all three types of data access patterns. So this is the motivation why we introduce a new file format. That's CarbonData. It's a single file format, but fits all different types of access. So to summarize our design goals, first, we would like to enable low latency for the three types of data access pattern we mentioned. Allowing fast querying on fast data is also a key here. As a file format, we would like to ensure space efficiency. Last but not least, we want to make it a general format available on the Hadoop ecosystem. So to highlight some key differentiator of CarbonData format compared to other column format which already exist on a big data platform. So CarbonData is a read-optimized columnar storage. So how we do that is we leveraging multi-level index for achieving a low latency. We can talk in detail later on. Supporting column group is another way of leveraging a benefit row-based as well as column storage. Enable dictionary encoding is a way for us to speed up aggregation queries so that we can defer decoding until a later stage. We also have optimization for streaming ingestion for fast data. Lastly, broader integration with other platform or processing engine on Hadoop ecosystem is our plan. So I have shared our couple typical use cases and the motivation and the issue we are trying to address. You may wonder how it works. So let's deep dive into the format itself and understand how it works. So at a high level, CarbonData file is structured into blocklet. So a blocklet is a set of rows stored in columnar format. And the column chunk is the data for one column or column group within a blocklet. And then at the bottom of the file, we have file footers, which store the metadata information of the file. So it might include statistic information at file level, a schema of the data, and the blocklet index. I'm going to introduce this concept a little later. So this is a file level index for us to speed up the scan. So in concept, a carbon file consists a sequence of blocklet. And then at the bottom of the file, we have file footers. So this is a very high level. So this is a visual representation of the file format. So you can see a CarbonData file contains a sequence of blocklet, and the file footers store meta information, schema. Blocklet index I mentioned is a file level index. So it contains information about min-max value of each column in the blocklet, and as well as multi-dimensional key index, which we're going to introduce a little later. We also store blocklet level metadata information. So for instance, we have a compression scheme of this blocklet, and column chunk length, column chunk offset, which is a pointer to the column chunk to speed up the scan. So let's deep dive into a blocklet. So how data is laid out in a blocklet. So not as other column format has done, we are not simply storing data in a column format row by row. We are actually sorting the data along MDK index. What do we mean is a set of columns will be picked to form an MDK index key. And then data along the MDK index key will be sorted globally across files. So basically, we are actually building an index here. The data itself is an index. We don't have a separate index for the data. The data itself is stored as index in column format. This is a key differentiator compared to other column format. There are a couple advantages of storing this way. So one of them is you can see data is clustered along the MDK index. Instead of scattered across multiple files, data are clustered probably in one file. So we can enable a very efficient scan over the data. Another benefit is we can build a file-level index to help us filter out the blockade we need to scan. I'm going to go into detail in next slides. So remember, I mentioned at the file footer, we have a blockade index stored. So this includes a blockade index node for each blockade in the file. So each index node contains the start MDK key as well as the end MDK keys, which also including a pointer to this blockade, as well as min-max index of each column. So at the runtime, we will leverage this file-level blockade index to build an in-memory MDK tree structure. And this tree structure will be utilized to filter blockade. So we can do a much better job than other column format only leveraging min-max. So we can narrow down the blockade we need to scan, and this is a major optimization for efficient scan. So besides a file level index I mentioned, we also allow you to build a column chunk level inverted index. So basically, within a column chunk, column data is sorted, and along with the row ID information embedded. So you can reconstruct the row back later on. This is generally suitable to low-cut analytic column because otherwise the row ID information overhead is too high. But with this inverted index, we can achieve a much better compression for this column because the data is sorted. Another benefit we see is fast predicate filtering. So with the help of the inverted index, we can quickly identify the rows within a column chunk we need to scan, as well as stitching them back, basically, because remember, we have row ID associated with each column data. So we can quickly stitch a couple of columns back much faster compared to other formats. So with the combination of file level index as well as column chunk level index, we have seen a substantial speed up in terms of querying carbon data. I also mentioned the column group concept in the outline of the file structure. So basically, besides using one single column for a column chunk, you can also allow multiple columns to form a column group to store as a single column chunk. This is more like a row-based format. So this is generally suitable for a set of columns which you can frequently fetch back. So the good thing is you can save the stitching cost for reconstructing the row. This is very beneficial for wide tables, and then you want to fetch a lot of column back. Next, we're going to briefly touch on nested data type support within CarbonData. So we support arrays and structs. For array, we represent them as a composite of two columns. So one column is for the element value itself, and one column is the star index and the length of the array, so that you know which row you are coming from. For struct, it's represented as a composite of a finite number of columns. Basically, each struct element is a separate column. So this is very similar to how ORC file format is supporting nested data type. As a file format, encoding and compression is very important. So we support quite a few efficient encoding schemes. So to name a few, Delta encoding, RLE, bitpact are supported. In addition, we also support dictionary encoding. So for medium-high cardinality value columns, we support a file-level dictionary. But for very low cardinality, we support a table-level global dictionary. So this is a big win for us because now with the global dictionary encoding, you can operate on encoding value all the way through the query stage until right before you return the result back to client. So speeding up aggregation is a key. Reduce it also because you're operating on encoding value, it reduces the runtime memory footprint. And the deferred decoding I just mentioned. With the global dictionary, we also allow fast distinct count by leveraging a bit set, which is an additional optimization we have done for distinct count. So overall, this global dictionary encoding enable us to have more safe I/O costs as well as CPU costs. So this is a big performance optimization. Besides the dictionary, we also support custom encoding schemes. So you can supply your own encoding schemes. For compression scheme, right now we support Snappy. We are planning to extend to others encoding compression scheme in the future. So with the combination of good encoding and the compression scheme, we can achieve a pretty good compression ratio as a file format. Now let's move on to talk about the frameworks we have integrated with CarbonData. So to give you an overview of how the module are organized. So at the very bottom, you can see we have a Carbon format. This is a format specification, which is a language agnostic definition. On top of that, we have Carbon core. This is a Java implementation of the file format with the basic reader and writer API. So with the Carbon core module, we essentially enabling to integrate with any other data processing engine or frameworks or data models. Currently, we have two modules built on top of it. So one is Carbon Hadoop. This is the Hadoop integration, which we provide a Hadoop input and output format. We also have a Carbon Spark module. This is the integration of Carbon with the Spark, and also including some query optimization we have done to leverage our format. So in the next couple slides, I'm going to focusing on the Carbon Spark integration, but the same logic can be integrated in any other processing engine or framework. So Spark integration. First, I'm going to talk about the read part. So how you can read a Carbon data file from Spark. There are two ways you can do that. One is through data frame API. So just like how you load some other file format like CSV, Parquet, error file, or JSON file to data frame. You can do the same for Carbon data. So after that, you can use a data frame. So after loading, it's essentially a data frame. Then you can do an analysis over data frame API. The other way of doing it is through Spark SQL statement. So just as how you create a Hive table through Hive context in Spark, you can also create a Carbon table through the context. After that, you can directly query it using a SQL statement. Besides that, we also support a schema evolution of a Carbon table. This is where alter table statement. So you can add, delete, or rename a column. So basically what it does, it doesn't change the data which is already stored on the disk. We don't make any change there. We are only make change to the schema. So next time when you query the data, it will be the updated schema will be effective and even for load. So let's say you actually load another chunk of data into this carbon table, this new schema will be recognized. So just touch a little bit more about optimization we have done for Spark integration. So for querying carbon data from Spark, first of all, we enable the vectorized record reading. So instead of reading row by row from carbon file, you now can read a batch of a record back. So that Spark enables Spark to do a vectorized execution. This is a big win. Another major optimization we have done is predicate pushdown. So not like any other column format done. We achieved predicate pushdown by leveraging the multi-level index we introduced in the format. So to give you an overview, at the driver side of Spark, you can also actually load the file footer of each file of a carbon table to build a table-level MDK tree index. This in-memory MDK tree index can be leveraged to identify the files you need to scan, basically. From there, once you identify the files you need to scan, and by leveraging a file-level blocklet index, you can identify the blocklet within a file you need to scan. Then by leveraging the inverted index, you can actually locate the rows you need to scan. So with the help of various level of index, we can do a much better job of narrow down the blocklet we need to scan and excluded the blocklet we can from the scan. So this is a big advantage of carbon data. Column pruning is achieved through columnar storage because we are column storage, so we only touch the columns which are interested to this query. We also mentioned about global dictionary encoding. So with the global dictionary encoding, we can defer decoding to a later stage of aggregation. So you instead of decode right away after you read the file, you actually can operate aggregation on encoded data. So this is a big optimization for aggregation type query. So in summary, this type of optimization we have done for Spark is applicable to any processing engine and framework. So we have seen some very significant performance speed up when it comes to query carbon data compared to other column format. So we're going to share some performance result a little later. We talk about read and write. Now we come to data ingestion, basically how you can write as a carbon file. So we support two major types. One is you can actually do CSV file conversion into carbon data through bulk data ingestion. There are two ways of doing that. So you can do a load statement through load statement or insert into table statement. So there are two MDK clustering level supported as well. One is a low level versus no level. So low level meaning all the data you have seen for this load statement, you're going to do a global sort on the MDK index. So this will involve shuffle, but it results in better clustering, but with the cost of congestion rate. So this two mode is a balance between whether you want to have a better ingestion rate or you want to have a better clustering. The other way of doing data ingestion is you can save a data frame as a carbon data. So after that step, you can query it through the optimization we have done. So one way of doing it is through data frame write API. So you can save a data frame into carbon data. So as we show an example here. So in general, carbon data is good at performing for big size of files. So data compaction is a tool we actually introduced to merge small files so that it operates on bigger files. This is also a chance for you to actually recluster the data across loads to achieve a better clustering along the MDK index. So two types of compaction are supported. One is minor compaction, which we only compact adjacent file into a single big file with the size of HDFS block size. So major compaction, on the other hand, which is a way for you to reorganize adjacent load, maybe multiple partitions, to achieve a better clustering along MDK index. Now we're going to move on to take a look at the performance result we have collected. Are you okay here?
Yeah, I think so. Okay. I'll use the other mic. Hello. Hello everyone, my name is Vimal and I work in the big data platform team at Huawei along with Ji Hong. So I'll take you through some the performance results which we have got with Carbon. So for the purpose of performance test, we've used a use case from one of our customers wherein the table consists of 300 columns and we've taken a data size of 2 terabytes. So as you can see from the chart that Carbon data is much faster than existing popular columnar data stores in most of the queries, almost all of the queries. So for the sake of clarity, we have categorized the queries into 3 types. As Jihang had mentioned, you have the high throughput full scan query, the OLAP interactive analysis query, and the random access queries. And in case of high throughput full scan queries, these queries usually access a subset of the columns. They don't access all the columns. They access only a few of the columns, but they don't usually involve any filters. So they scan through your entire set of data. So in this case, we had the data set of around a little over 1 billion records. So this is the result of scanning for 1 billion records. You can see Carbon data is 1.4x to 6x faster than existing popular stores. And in case of OLAP interactive queries, the queries usually involve a subset of the columns, but they also do involve some filters and grouping expressions. In this case, Carbon is around 20 to 33 times faster than existing data stores. These are actually preliminary results, so these are not yet official. And the final case is the random access query, where you can see the huge difference between Carbon and other data stores. So these are the queries in which user usually selects all of the columns, but applies some filter which narrows down the result to very few rows, and there's no grouping involved here. So the observations from the performance results is that in case of high throughput full scan query, most of the performance benefit has come from the deferred decoding feature. Almost all of the columnar data stores use some kind of encoding to encode the data, to reduce the data, to achieve better compression and better storage organization. So, but what happens is when you are running a query and the data is being read from the disk element by element or cell by cell, the data has to be decoded on the fly. And the decoded data is much bigger than the encoded data, and all operations are performed on the decoded data. But in Carbon, what we have done is we have designed the encoding in such a way that you don't need to decode the data immediately. So we read the encoded data, we don't decode it immediately, we do all the processing on the encoded data. So we save a lot of time in that you don't need to decode each and every record, you just decode the final result, which is much lesser and aggregated. And since the encoded values are much smaller, you need less memory space and less CPU to move around the data and play do some computation on the data. So that's why we are getting this performance improvement. And in case of OLAP queries, they definitely involve a lot of filters. And in case of filters, indexes come into play. And we have MDK index and min-max index, which helps us to locate a subset of the blocklets which may contain the data. And we have inverted indices at blocklet level, just like Jihong explained. And these inverted indices help us to locate the rows within the blocklets that may contain the data. So these indexes together help us to eliminate a lot of unwanted I/O and help us to read the required data much faster instead of wasting a lot of time in reading the data that may not be actually required. And since these OLAP queries also involve a lot of aggregations and group by, deferred decoding also helps here. And we have the random access query. In case of random access query, as I told you, the queries select almost all of the columns in the database. So in this case, we have 300 columns. So these queries either do select star or select more than 150 columns. And in these cases, and these queries also do involve filters. So definitely the indexes come into play. They give a lot of improvement. But what we have observed is most of the performance improvement comes from a different aspect. This is something no one tells you about columnar data stores, is that in columnar data stores, the data is stored in as many column chunks. They don't store the row together. Instead, the columns are stored together. So what happens in this case is if you want to read a row, say suppose you want to read row number 5, you need to pick the item number 5 from column 1 chunk, item number 5 from column 2 chunk, item number 5 from column 3 chunk, and you need to stitch them together. This is called implicit join. And it sounds simple, but when you are doing a lot of encoding on the data, the picking up a required element from a chunk is not so easy. So it involves a lot of computation overhead, and this is why other columnar stores are slow when you are accessing a lot of columns. So we have something called inverted index, in which we store the row ID also, which helps us to reconstruct the row faster. And we also have another feature called column group, wherein we allow the user to configure a set of columns to be stored in row format. So such columns will not be stored in columnar format. Instead, they'll be stored in row format, which completely eliminates the need for row reconstruction. So now I'll give you a quick live demonstration of Carbon versus existing popular columnar formats. So for the purpose of this demonstration, we have created a cluster of 5 VMs in AWS. We have used R3 for large nodes. Each node has around 16 vCores. Totally, we have 80 cores. And we have allocated around 100 GB per node. So we have a total of 500 GB. And we use the same data set of 300 columns. But we've used considerably smaller data of 600 GB. The total record size is slightly more than 300 million. So I have created a connection through Beeline, this Hive client. So for the live demo, I'll give a sample of each type of the query. First, I'll give you an example of high throughput full scan query, then the OLAP interactive query, and the random access query. So in the high throughput full scan query, as you can see, it's a simple query wherein we select 2 columns, the brand name and the order quantity. And we want to see the number of orders which have come for each of the brand names. So let me run the query on Carbon first. So I have the query here. I'll just copy it and paste it here. So you can see the query ran in around 1.7 seconds. And I'll try to run the same query on the default columnar store in Spark SQL. So I've created 2 tables, one a Carbon table and one based on the other columnar store. So I'm running the same query here. So you can see it's taking considerably more time. Yeah, it took around 10 seconds. So that's a difference of almost 8x. And coming to the OLAP interactive query, you can see the query has a considerable number of filters. And what we are trying to do is we are trying to find the number of orders which we have received for different colors of Huawei Honor 4X phone. from country is New Zealand and city is Auckland. So we are applying filters on the country and city and the product name. And we are trying to group by the product color. So we'll run this query on Carbon. It came in 800 milliseconds. And let's run the same query on the other store, the default in Spark SQL. Again, it's taking more time. So the advantage that Carbon gets here is from the indices. Because of our indexes, we are able to quickly locate the block that contains the data for New Zealand and city Auckland. And not just the block, it's also able to quickly locate which rows in the block can contain the data. And after we retrieve the records, the deferred decoding helps us to aggregate the result much faster. And coming to the random access query here, you can see the query involves select star. So we are selecting all the columns, and we are applying a huge number of filters, and there's no group by in this query. So it's going to scan all the 300 million records and return a very few number of records. So let's run this query on Carbon. So it took around 3 seconds, 2.8 seconds. And since I've run this query previously on the other store, I must warn you, it takes more than 10 minutes. So let us still run it here. OK, since it's going to take more than 10 minutes, I'll go back to the presentation, and probably we'll come back after we are done with the presentation. So that was the demo. And now let's talk about the future plan of Carbon. So Carbon is in a beginning stage, though it's completely stable and it has sufficient number of features for production use, and we are using it in production in many of our sites. But still, we have a lot of plans for Carbon. We want to upgrade to Spark 2.0. Currently, we are integrated with Spark 1.5. And Carbon is mostly read optimized in the sense that you cannot do insert, update, and append operations. We do support append, but in that case, it creates a new store file, and it's like a batch append. We want to support streaming append, wherein you can append real-time data, wherein what we could achieve is we could reduce the latency between the time the data is created and the time the data is available for analysis. And to further enhance the performance, because as you had seen, some of the queries are still taking 2 seconds, 3 seconds. But many of the interactive analysis cases, the expectation is sub-seconds. So the users expect the query to come in 500 milliseconds or so. So we are planning to have support for pre-aggregated tables, wherein we'll have some built-in mechanism to have certain pre-aggregated tables which would be populated when you're loading data into the main table. So when you make a query, if the query columns in the query match that of the pre-aggregated table, instead of scanning the original table, the engine would scan the pre-aggregated table and return the result. And we want to make it transparent to the user in the sense that user need not specifically give the name of the pre-aggregated table or need not be even aware that the pre-aggregated table is there. And we also plan to support insert, update, and delete. This is majorly for enterprise customers who actually not just want to do analysis, but also want to support slowly changing data. And we also want to build a diverse ecosystem for Carbon. And for that, we plan to integrate with a lot of different query engines and data stores in the Hadoop ecosystem. And that's our future plan. And we'd like to build a vibrant open source community around Carbon. So we've already open sourced Carbon, and it is licensed under Apache license. And we'll become an Apache incubator project quite soon. And you're welcome to check out the code from our GitHub page. And please download it, test it. And if you have any queries, just post it to us. And if you find some bugs or something that you can contribute, feel free to contribute. You're always welcome to do that. And we would like to thank all of our contributors, all of my team members from Huawei, and members from other companies like Gene, Henry, and Uma from Talent, eBay, and Intel, respectively. And with this, I would like to end the presentation here. And I would be happy if you can ask any questions. Yeah? Right, right. Yeah, it's a good question actually. Compared to the other data stores, we do a lot more work during computation. Though we have optimized a lot, it still, you can say, twice the computation effort of other stores. So during the write time, there is more cost involved, but it's much offset by the maybe 10x to 600x benefit which you get during the query time. Yeah. Yeah, actually, we used a popular data store which comes in Spark SQL, but since the results are not very official, it's in a preliminary stage. We don't want to give the name, but soon, once the results are officially verified, probably we can disclose the name. Yeah, it's on HDFS. It's ephemeral HDFS on AWS.
Go ahead.
Sorry, your voice was not audible. Not fixed width, in the sense it's kind of variable length data types like strings. So the different rows can have different number of different length of the cells, but the number of columns are fixed. It's like a structured data store. Okay, thank you everyone. Thanks for attending our session. Yeah.